Welcome back to your favorite class, etc., etc. Raw or dynamics, yay. Just what you all were thinking. All right. Dynamics. Let's do it. Today, new topic, gears, which is why I've included this awesome picture from the New York Times. What's wrong with this picture? Since we're starting our topic on gears. No meme today, just a crazy picture. Who can do it? Those gears will lock up.
It's gear locked.
Yeah, it ain't gonna move. Yeah, what the hell? New York Times, what are you doing? I don't know if they meant to do this on purpose or what, because they're trying to symbolize a seizure in the NAFTA trade agreement, whatever, between the United States and Mexico and Canada. But I think it's pretty ironic that the New York Times and the editor and the journal itself are just it's okay. No one cares about real mechanical systems. It doesn't really matter. You think they could have separated some of the gears just a little bit to understand that we're trying to all kind of work together for some accomplished goal, but no, I guess that's not the case. All right. David, did you mute your microphone again, David? It's still got some sound in my ear. Oh, anyway. All right, we're talking about gears today. Just a couple announcements too as a reminder. Your first simulation or your third simulation for the class is due next Friday. It's on linkages, so make sure you take a look at that. The linkage material is done for the class, so you've got everything that you're going to get from me on linkages. So do that. Homework number 7 on gears. I haven't quite given out yet, but I will give out probably the beginning of next week. Is going to be due a week from this upcoming Tuesday. And then your final exam for this class will happen on Thursday, May 21st, which is 3 weeks from yesterday. Okay, so not a lot left. Only these 3 little things that you got to do, including the exam. So do that. All right. Gotta see if I can figure out this feedback issue. Sorry, just a second. I'm having technical difficulties. All right, I'm gonna have to come back. I got a feedback in my headphone. All right, I'm back. Did you miss me? Be honest. Okay, I know you did. All right, so let's get on with the dynamics. We have no leader. Anarchy begins. What, someone else is going to teach you how to do gears? It's so complicated. Oh, I'm just kidding. It's not that complicated. But I had to get a PhD to teach it to you for whatever reason I'm not sure of. All right, gears or gearing systems. We're going to kind of have to spend some time on the front end here just working through vocabulary, which, is a little bit sucky. We're going to just have to introduce them a little bit and talk about some verbiage associated and some typical gear systems. So not really getting into the depth on the math a little bit too much. This lecture might be a little slow, but we'll get there with a little bit more depth on the lectures to come. All right, so gearing systems. Away we go. Hopefully we have all seen gears in some sort of capacity in our life before, but the most general model would be something like this. Bam. Gears. And this is as simple as it gets. All right. One gear is being driven, often called the pinion gear, and the other, one gear is driving and the other is driven. So the one that's got a motor that's sort of in control of the whole system, that's the drive gear, or what's called the pinion gear. And this guy, who is sort of interlocked with that, is going to respond to it and have some translational or linear or rotational motion of its own. All right, so these gearing systems here are rotating machines with these teeth that allow interface between what would be shafts otherwise. All right, so these are rotating machines with teeth. that interface to transmit rotational motion. And torque. All right, this is the big one, the torque. A lot of people understand that if you have one gear that's smaller than another gear, that the angular velocities of the two will be different just because, you know, one is bigger than the other. So a lot of people understand that you can use gears to sort of step down or step up an angular velocity appropriately of your two shafts that are connected to these gears. But a lot of people lose sight of the fact that there's also a different amount of torque that your shafts can now handle, or torque that you're transmitting with each one of your additional shafts because of this gear ratio. So you can change the angular velocities of these two shafts that are connected to these gears, obviously, but you can also change the amount of torque that each one of these shafts transmit, and that is often lost in the wash when people are too busy thinking about angular velocities of these guys. All right. So they change output speed and torque of connected shafts. All right, that's kind of what they're useful for, what they're good for. Where they're touching each other is called the mesh point. All right, so where they're touching each other, here in this particular example, I guess is like right there. That's your mesh point. All right, or sometimes just called the mesh. We typically talk about these systems in terms of the number of gears that are together in sort of a chain. And so the number of gears that are aligned in a chain is called a gear train. All right, so interlocked gears. Is a gear train. All right. Often referred to by the number of gears that are in the gear train. So up here, we have a 2-gear train. Yeah, I had to get a PhD to teach you that. Yep. 2-gear train. I'm highly qualified to teach you about 2-gear trains. All right. Usually, one gear drives the train. Choo choo, baby. We're driving the train. Sometimes you could have 2 gears in a chain, like in a chain of, or a train of gears that are both being driven by some motor, but that's usually not the case. It's kind of like the analogy of like 4-wheel drive. All right, sometimes when you have 4-wheel drive, power transmission occurs not just to, like, let's say the front wheels, but also the back wheels as well. So driving your car with all 4 tires. Not really the most efficient, because in some situations they might be fighting against each other. The same idea with like gear trains and gears that are in a series. Usually you'll have one guy that's kind of like driving the entire chain, but you might have a situation where there are 2 guys that are kind of driving this thing because you just need like extra power transmission sometime down the line. So usually one gear drives the train, but sometimes you might have multiple gears driving. All right. So enough of that introduction. Let's talk about some common gear types, or the nomenclature associated with gears that you've probably seen in your life. All right. So gear types. The most common by far, and what we're going to talk about in this class, is the simple spur gear. All right, in a spur gear, let's put a picture of it up here. I like actually having the white pad for this particular lecture, because when I used to do this on the whiteboard in person in class, I would have to draw this. And yeah, suspicious. Let's just say, to be the least, suspicious. But here, these spur gears, you have these teeth, which are sort of being represented by these solid black lines in this picture. And they're all sort of parallel or in the same general direction as the shaft of this particular system where the gear is attached. All right, so let's make that point here, is that for spur gears, the teeth are parallel to the shaft. All right, so we can sort of see that happening in both these particular gears. All right, so parallel teeth, and they're used to transmit motion between parallel shafts. All right, everything is parallel. The world is right. Rawr. All right, this is what we're primarily going to analyze in this particular class. All right, parallel teeth, parallel shafts, very simple idea. The next level up in complication from the spur gear is the helical gear, which looks very similar, except now the teeth are not necessarily parallel to the shaft. All right, so the next level, we just leveled up. Pretend it's a video game. I know you guys are probably playing a lot of video games these days because you got to stay inside. Rawr. All right, our helical gears. All right, so these are still kind of transmitting motion between usually parallel shafts, but not always. And here, the teeth are not necessarily parallel to the shaft. So here's our helical gear. Let's see if I can make this bigger. All right, here's your helical gear. And unlike the spur gear, which had these like parallel lines, now we have the helical gear, which has these lines that are kind of like at an angle. These teeth are at an angle with each other. And so they have to marry up appropriately, so you sort of see the teeth that are offset as such. Right. These are basically the same as spur gears with a couple of caveats. All right. But the differences are less noisy. So if noise is a concern for you in an engineering application for whatever reason, your helical gears are less noisy. And that's because when the teeth are interfacing with each other, it happens gradually, right? So you have one tooth kind of moving into each other in sort of like a wave type motion where it's not necessarily just hitting all at the same time, right? So with these spur gears, it's like, you know, the spur gears themselves, you have these teeth that are parallel with each other that will come into contact with each other at a discrete location all at the same time. So with the spur gears, it's like bang, 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 bang. Okay, but with the helical gears, it's more gradual, right? It's like a slower motion, and that creates a sort of this like less noisy situation. Okay, another way in which they differ is that when you have helical gears, there will now be force that's transmitted along the axis. All right, and that's easy to see. So if this guy happens to be rotating like in this general direction with this angular motion, then this guy's going to kind of be like rotating sort of in this direction, and what that's going to do is that's going to cause force on this particular gear, which is normal to that particular tooth. So right at that interface, that gear is going to want to like push on the other gear in that general direction, and to fight back, this guy is also going to have to push back on that guy with sort of a similar magnitude. And what that results in is at this particular time, like one pushes on the other and they have to like push back against each other. So what's going to happen is this guy is going to kind of want to try to move generally this direction, and this guy is going to kind of want to generally move this direction. So if you don't have them secured in this axial fashion and you try to spin them against each other, they'll just slide against each other and won't actually transmit any angular motion. So need axial restriction. That's usually accomplished by some bearing that can accommodate axial thrust. So an axial thrust bearing is common for helical gears. All right. Lastly, the way that they differ is that obviously the teeth are not parallel to the shaft. And so shafts don't need to be parallel. meaning that you can transmit motion between these types of gears with shafts not being parallel to each other. So for the spur gear, we saw that they had to sort of like be parallel with each other to sort of like transmit any motion. All right, so think of like these two little pen caps as like these spur gears rotating with each other. All right, not the case when you have the helical gears, where they could be sort of at like some weird angle like this and still transmit motion between themselves. Just now, there's axial force that's being generated in those guys. All right, so there you go with your helical gear, or sometimes it's called a helical spur gear because it looks a lot like a spur gear, except it just has these angular teeth. Next is bevel gears, which are angled or transmitting information between shafts that are 90 degrees with each other. Next, bevel gears. Rawr. Get on my bevel. So you've probably seen bevel gears before. They look like this. Again, I don't have to draw it. It's really nice. You should see me try to draw this one on the board. Yikes. Very suspicious. All right. Here we've got an interface between shafts that are 90 degrees with each other, or they don't necessarily have to be 90 degrees with each other, but that's the most common situation. All right, so here teeth are formed on a conical surface. All right, so the conical surface of interest here, if you're looking from the top, like this triangle here is like the side projection of a cone, right? Where this is like the base of the cone and it's coming to a tip right at the center here. All right, so hopefully you can see that conical surface. And if that's the case, then here are the teeth that are lying on that conical surface. All right, so there's your teeth on a conical surface. And what this allows is this allows you to transmit this information between shafts that are 90 degrees to each other, right? So in this particular case, they're 90 degrees with each other, but it could be some other angular position as well. All right, so transmits motion between intersecting shafts. Or like what would be intersecting shafts. All right, so if we thought about like this shaft here would intersect with this shaft here, so you have to input the gear here so that we can transmit the power and the angular velocities appropriately. All right, so intersecting shafts, bevel gears. I used some bevel gears this summer. It's kind of a cool little project that I was working on. So common for transmitting information from things that are like 90 degrees apart. All right. We have one specific type of bevel gear that's a little bit crazy. And so this is kind of like a standard bevel gear. And you could have a crazy sort of situation where the shafts aren't necessarily in line with each other. So the shafts are offset and they don't necessarily have this standard conical pattern. So here's a crazy example of a bevel gear that's a little bit more complicated. And this here is an offset hypoid bevel gear. So let's talk about this for just a second. So again, they're intersecting shafts that are 90 degrees from each other. So here's shaft number 1, and then into the board here is kind of shaft number 2. And what I say when I mean offset is that the planes or the center axis of the shafts of these two different systems are not on the same plane. So they're offset from each other. Right? And then it's hypoid because it has this very strange like alignment of teeth. So we see like this angular alignment of the teeth, and these are hypoid teeth. So this guy here is called a hypoid, or sometimes called a hypoid offset bevel gear. D is not as common, but sometimes when you're in tight, confined mechanical spaces, you don't have a lot of options. So sometimes you need some crazy looking teeth and crazy gears. So like, look at the teeth on this thing, man. That's crazy. Like how spiral looking they are. I mean, to manufacture that thing would be, God, a pain in the A. All right, so you got to manufacture those gears. They're freaking expensive, man. Even like Spur Gears by themselves are expensive if they like conform to proper standards. Man, like just a standard Spur Gear costs like $50 for a tiny little Spur Gear. So if you're talking about like these high point bevel gears, they're like hundreds of dollars to get like this system going. So, god damn, expensive, right? I ain't got that kind of money. I'm just a teacher. They don't pay me the big bucks. They pay me the little bucks, but at least they pay me some bucks. Lastly, is going to be another system that pops up from time to time and, you know, is in your vehicle, and that is the worm gear. All right. And the worm gear allows you to go from linear motion to angular motion. So here's a picture of a worm in a worm gear. And the idea here is that you want to drive this. Here's your worm. And here's your worm gear. Is that you want to drive the worm kind of in this linear fashion. So if I move that worm in a linear way, it's going to sort of cause the teeth to make the gear turn around. All right, so linear motion here will excite this angular motion because of the way that these teeth here kind of looks a bit like a screw are sort of digging into that worm gear. All right, so this linear motion translates to angular motion of something. All right, so allows, resembles a screw, and translates linear motion to angular motion. Can also be done with a rack and pinion in a similar way, but worm gears are more exciting. And this is a very common apparatus that is used for your windshield wipers. All right, so you think about your windshield wipers, there's a worm gear here that's attached to the base of your windshield wiper. And so when you push that worm gear and sort of cause it to spiral, your windshield wiper does this. And then when you pull it back, it comes back. So you have this sort of like motion that causes your windshield wipers to move. So that's how your windshield wipers work. Congratulations, I just taught you something new, probably. Unless you're like a car junkie and already knew that. Maybe some of you are. All right, mechanical engineers, likely some car junkies out there that already knew that. But it's a general idea. You have non-intersecting, non-parallel shafts, and you're transmitting information. Non-intersecting, non-parallel shaft transmission. There you go. It's like the extreme example of this hypoid bevel gear. The teeth look very similar on this worm. It kind of looks like a screw, and it's an extreme example of like this situation here. All right. So there's your worm gear and worm. All right. Now we got to get into a little bit of boring stuff, and I'm sorry that it's going to be boring, and I'm sorry it's not going to be that exciting. We have to go through some nomenclature because part of this class is being able to use vocabulary correctly to describe gears. So we just got to go through it. All right. So buckle up, get the coffee, stay awake while we go through some vocabulary that might not necessarily be as exciting. All right. So we got to go through some nomenclature. And before I kind of dive in on this nomenclature, I'm going to put up a picture of this gear and these gear tooth, because I think it helps a little bit to sort of see the picture and talk through the picture when we're introducing this general vocabulary. All right. So here's our picture, and I'll kind of refer back to this picture as we go, instead of trying to draw it myself. You don't want that to happen. We've all seen what happens when Dr. Hart tries to draw pictures. It ain't pretty. All right. So first things first is we got to talk about the pitch circle and the pitch diameter. So pitch circle is the circle upon which all of these gear calculations are based. All right, so we can see that in this particular image here is this pitch circle. All right, so here's some teeth on a gear. We see the pitch circle, which is like this line here, and so this is like, I guess, a partial pitch circle, and it is the location basically in the center of the teeth where we say is like the interfacing or the meshing point between the gears. All right, so that's the pitch circle for this particular piece, and in English we would say that this is like the theoretical circle upon which calculations are based. All right, so there you go. It's this pitch circle, and this pitch circle has a pitch diameter. And obviously it's the diameter of the pitch circle. All right, so again, here's my pitch circle. And if this kind of went all the way around, imagine it went all the way around, then the diameter of that guy would be the pitch diameter, right? Hopefully that's understand. Again, PhD required to teach this too. All right, next, the pitch circle, not to be confused with the circular pitch. How could you get that confused? All right, the circular pitch is the distance between teeth, and not the space between teeth, but the distance between the same point from one tooth to the same point on the next tooth. So picture, here we are with our circular pitch. If we have like this point on this tooth, then the distance between that point and that same point on the next tooth is the circular pitch. Notice that's not the distance between teeth, it's more or less the distance that you have to go from one tooth to the next. All right, so distance from one tooth to the next. All right, there's your circular pitch. All right, usually given by the variable little p. Sort of hard to draw a little p and a big P. That's a little p. All right, continuing. The module. Module's not on this image, but the module is also related to, and I'll put this on here as well, the diametral pitch. Let's do the diametral pitch first because it's a little bit easier to understand. The diametral pitch is the pitch diameter. Okay, so remember the pitch diameter up here. This is the diameter of this circle. So again, here's our pitch circle, and the diameter of that circle is something like that. So the diametral pitch is the number of teeth divided by the diameter of the pitch circle. All right, usually the diametral pitch is assigned to the variable capital P. So this is capital P, is the number of teeth divided by the diametral pitch. So this is like the number of teeth N divided by the diametral pitch D. So here is number of teeth. And D here's the diameter of pitch circle. So it's like how many teeth are there in your gear divided by the diameter of that gear. One thing that you'll note about the diametral pitch, and this is probably the most important takeaway here, is that mating gears must have the same diametral pitch. All right, so this diametral pitch is an indication of like how coarse or fine your teeth are on your particular gear. So if I have a gear over here with a diametral pitch of 2 and a gear over here of a diametral pitch of 20, Well, the gear over here with a diametral pitch of 20 has very fine teeth on the outside of the edge of that gear. And the diametral pitch over here of 2 has got very coarse teeth on the outside of it. So you try to mate those up and it's not going to work, all right? Those teeth won't fit into each other properly. So you got to make sure that you have this proper diametral pitch or else it's not going to work. All right, so let's get back then to the module, which is the inverse of diametral pitch. All right, so M is 1 on capital P, or you might see it as M is equal to D on N, where D is the diameter of the gear and N is the number of teeth that you have. All right. So there you go for module. Sorry, I'll put that back up here. It's the inverse of diametral pitch. Little m is 1 on capital P. This is the same thing as D on N. Done my Perrier today. I'm so parched. If only someone would deliver Perrier to my apartment. I live at 123 Awesome Street if you want to send some to me. All right. Last things we'll talk about for nomenclature, for vocabulary, is the addendum, the dedendum, and the depth. All right. The addendum is the distance radially between that pitch circle and the top of the tooth. So let's go up here. Here's your addendum. All right, it's the radial distance between your pitch circle, remember, which is here, and the top of the gear tooth. All right, so here is your addendum. You got your own addendum. All right, there's your addendum. Dedendum, similar, except from the circular pitch to the bottom of the tooth. The tooth hurts. All right. All right, so there you go. It's the radial distance from the pitch circle to the top of the tooth. The dedendum is the radial distance from the pitch circle to the bottom of the tooth. And the whole depth is the addendum plus the dedendum. So this is basically like the total tooth height, if you want to think of it that way. All right, so the whole depth is just like addendum plus the dedendum. So here's like the whole depth of the thing. All right, there you go, addendum plus dedendum. Now we got our definitions. We got our nomenclature. We got information squared away. All right, some additional mathematical relationships that you need. That you might need. We already talked about the relationship between the diametral pitch, the number of teeth, and the pitch diameter. All right, so let's remind ourselves what that is that diametral pitch is equal to number of teeth divided by pitch diameter. In symbolic form, that is diametral pitch, capital P, is number of teeth N divided by pitch diameter, little d. All right. So we've already talked about this. The diametral pitch of 2 mating gears must be the same. Otherwise, they can't drive each other. If the diametral pitch of one is greater than the other, then the first one has more teeth on the outside than the second one can handle appropriately. All right, so have to be the same from gear number 1 to gear number 2. Another relationship that we have is between the module and the pitch diameter and the number of teeth. So we've drawn that already, is that the module is sort of the inverse of there. It's the pitch diameter divided by number of teeth. So M is equal to the pitch diameter D divided by number of teeth N, which again is 1 over the diametral pitch capital P. Most of the time, the diametral pitch is prescribed for gears, but sometimes with data sheets, you see it as the module. So they give you the module, and you're like, where's my diametral pitch? How do I know how to make this gear? Okay, well, it's 1 on that number. All right, let's remind you, diametral pitch here is going to be in units of like 1 on inches. And module, sorry, did I have this right? Yeah, it's going to be in units of like inches. All right. Example units there. Lastly, this is the circular pitch. This is the circumference of the pitch circle divided by the number of gears. So circular pitch here is equal to circumference of pitch circle divided by number of teeth. All right. So here, circumference of the pitch circle is just pi times the diameter of the pitch circle. So this is pi times little d divided by capital N. All right. You might also see it as pi divided by capital P. Because remember, capital P is capital N on D. All right. So these are some of the basic mathematical relationships that you need to know kind of off the cuff and that we're going to use in calculations quite a bit. All right. So let's see one example calculation really quickly, and then we'll get you out of here on a Friday. Get out and enjoy the 41-degree weather. Oh, come on, man. Let's go, Wisconsin. It's like mid-May. God damn. Imagine if they're like playing baseball right now. It's like 40 degrees out. God, annoying. All right, let's do an example problem. All right, example problem. And this example is in the slide deck in the notes. I'm just going to copy it down by hand here because it's not going to take too long. So here we have an example. And we're given information about one gear that's driving another. All right, so we have a spur gear with 16 teeth. All right, and it's got a diametral pitch of 2. Driving a gear with 40 teeth. And we're assuming that it's mating up well and there's no errors or no issues. All right, we want to find the following. Number 1, we want to find the circular pitch. Okay, this is how many teeth there are per inch on the outside of each one of these gears, which should be the same if they're mating with each other. And we also want to find 2, the center to center distance. Between gears. All right, so let's get at it. First part, we want to find the circular pitch. So let's remind ourselves what the circular pitch is. All right, the circular pitch is the distance on the outside between teeth. Distance between teeth. All right, all the way back up to our picture, our circular pitch. Here it is, sparkles. Rawr! All right, it's the distance from like here to here, the distance between gears and exact same points on both of those gears. Well, if we know how many teeth are on the outside of the gear and we know the diameter of this particular gear, then we can calculate the circular pitch. All right, so the circular pitch here is going to be little p, which is going to be like something like pi divided by big P. All right, so here we have pi divided by 2, and this here is inches inverse for the diametral pitch P. So this will leave us with a circular pitch, which is the distance between adjacent teeth on the outside of this particular gear. It's going to be 1.57 inches. Right, so there you go. For the circular pitch, it's the distance between teeth on the outside. 2. Now we need the center to center distance between these gears. Center to center distance. All right, so if I have like this 16 teeth gear, usually with 16 lowercase t, and here I have it mating with a gear that's 40 lowercase teeth, I want to know what is the center to center distance here. So here this is center to center distance, and usually we abbreviate this with capital delta. All right, so that's the center to center distance that I'm looking for in this particular situation. So if I need the center to center distance, I'm going to need what is like the radius of each one of these particular gears. And so to get the radius of each one of these gears, I'll get the diameter of each one of these gears, which is the the pitch diameter of these particular gears. So we need pitch diameters. All right, so I need to know like what is the diameter of this 40-tooth gear and what is the diameter of this 16-tooth gear. All right, well I can do that if I know what the diametral pitch is and I know the number of teeth on this particular gear. So if that's the case, then the diameter of the 16-tooth gear is going to be the number of teeth that I have divided by the diametral pitch. And this is just kind of like the inverted relationship that we learned for the diametral pitch P. So remember that capital P all the way back up here is the number of teeth divided by the pitch diameter. So if I'm looking for this little d, then I can just sort of change this relationship or invert this relationship, and it'll be capital N on capital P. All right. So for the 16-tooth gear, I have 16 teeth. The diametral pitch is 2 inverse inches. And so this will end up giving me a diameter of the first 16-tooth gear of 18 inches. Similar idea, the diameter of the 40-tooth gear, I have 40 teeth here. And because they are mating with each other, they must have the same diametral pitch, which is 2 inverse inches. And so you're going to end up here with 20 inches for the diameter of the 40-tooth gear. All right, so this guy has got a diameter of 20 inches. This guy has got a diameter of 8 inches. Right. So if that's the case, then the total center to center distance, delta, is the radius of the 16-tooth gear plus the radius of the 40-tooth gear, which here is going to be 4 inches plus 10 inches, which is going to be 14 inches. So if you're spacing your gears or anticipating needing to space these gears appropriately, you need 14 inches center to center between the two different shafts. Bam! There you go. Introduction to gears, very simplistic, a lot of vocabulary, a lot of mathematical relationships that we have to get out of the way, but you know, it is what it is. It's our first foray into gears, and there's lots of nomenclature associated with gears, which you will find. All right, that's it for today. Thanks for coming. Hope you have a great weekend. Get outside if you can. Stay away from people. Rawr, rawr, rawr. Which is little p, which is big P. Lucas, capital P is diametral pitch. That is, I know it's hard. It's like really hard to show. This is a capital P, right? This is the diametral pitch. It is the number of teeth divided by the diameter of the pitch circle. Complicated. Little p is the circular pitch, which is the distance between teeth on the outer edges of the gear. I know, it's annoying. Maybe I should do something special like with the cap P and the smaller p. Maybe I'll figure something else out for next time. Aaron, it snowed by my house today. That sucks. Yeah, it snowed here a little bit today too at like 11. I live in downtown right by MSOE. Because I'm lazy and I don't want to live far from work. make gears great again. I just saw that. That's funny.
Dr. Hart,
Yes.
this is like a completely random question.
Well, it's going to be a completely random answer.
Do you know who teaches like the material science curriculum?
Do I know who does it?
Yeah,
Yeah, of
like
course.
just like the professors who usually teach it.
Yeah. So Matt Schaefer's big on teaching those classes. Cindy Barnaky teaches a lot of them. Um, that's mostly who I know teaches those classes. Why do you ask?
Oh, I'm just like there's like an ME staff thing and I had to like put that there. So like it's not really determined who's teaching that. So I was just wondering like which professors I should be expecting.
I think maybe they're trying to figure it out. So Cindy, I know, gets wrapped up in a lot of like administrative stuff because Dr. Barnaky gets wrapped up in a lot of administrative stuff a lot of times because she's the head of the IE program, the general engineering program that they have for evening hour students. And so sometimes they keep her just like as a floater to maybe teach night classes for some students that need it. But if they don't have a lot of students that need night classes, she'll like probably teach the material science class. Otherwise, sometimes they hire like adjuncts to fill some of those roles if they need to. I think they have a couple on retainer, though I don't know really who they are very well. But I'd say the most likely bet is that either Dr. Barnaky or Dr. Schaefer will teach the material science class, though, don't hold me to that.
Okay. That helps a lot.
I better stop this recording.